In this video, we are going to examine use of curved arrows in organic chemistry. Curved arrows are used to indicate movement of electrons. We sometimes colloquially call it pushing electrons. And they are used for two purposes: to indicate movement of electrons in space and movement of electrons in time. Movement of electrons in space is electron delocalization. So in that case, electrons are delocalized over more than one bond or more than one atom, and then we use curved arrows to indicate delocalization. That is something we will cover later in the course. What we are now more interested in is movement of electrons in time. So use of curved arrows to indicate movement of electrons in time. So to show flow of electrons in the course of reaction, we use curved arrows. Movement of pair of electrons is indicated by full curved arrow. Movement of a single electron is indicated by curved half arrow, or as it's sometimes called, fishhook arrow. Full arrows indicate movement of two electrons, and they always have to follow each other in head-to-tail fashion if more than one is used in a course of mechanism, and frequently that is the case. Simply, a free electron pair is moved to another orbital that is empty or will be empty, and another electron pair is moved away from it. Movement of two full arrows towards each other would mean that we are pushing two electron pairs towards each other, or one on each other, and that's obviously not possible because of the electrostatic repulsion. And same would be with movement of two arrows away from each other. Then we would be simply attempting to move one electron pair in two directions, again not possible. So they have to follow each other. On the other hand, fishhook arrows always point either towards each other or away from each other. That's because they indicate movement of single electron. So when they point towards each other, that's bond formation. Two single electrons are pairing up to form a bond. When two fishhook arrows or half arrows point away from each other, that's bond breaking. A bond is broken homolytically so that two atoms split up and each carries one electron with it. Of course, we have to make sure that we use curved arrows correctly. Curved arrows are used to indicate bond formation and bond breaking. So here are a couple of examples of formation of sigma bond, where curved arrows are used to indicate movement of a free electron pair into an empty orbital, resulting in formation of a sigma bond in each case. You should make sure that you understand these examples and that you can follow flow of the electrons so that you know which bond has formed as a result of indicated movement of electrons. In the first case, it's the OH bond that has formed, and in the second case, of course, it's phosphorus boron bond that is formed as a result of indicated movement of free electron pair. In this example, we have formation of a pi bond. So free electron pair is moved in the space between the two atoms, between the two carbons. We can see that carbon on the left has free electron pair and carbon on the right an empty orbital. So now we move free electron in the space between two carbons, and the result is formation of pi bond, of second bond of the two bonds that form a double bond. And then we have examples of bond breaking. So here is breaking of a sigma bond. So curved arrow indicates that a hydrogen-bromine bond is broken in such a way that electron pair ends up on bromine atom. So we end up with proton and bromide anion. And in the second case, we have an example of breaking of a pi bond. So carbon-oxygen pi bond is broken in such a way that free electron pair ends on oxygen atom. That's what curved arrow indicates. Frequently, curved arrows indicate simultaneous bond formation and bond breaking. So here we have breaking of carbon-carbon pi bond. So pi electron pair from a carbon-carbon pi bond flows to form carbon-carbon bond. So curved arrow starts at carbon-carbon pi bond and ends on electrophilic carbon. Carbon is electrophile, carbocation. And so new bond that is formed is carbon-carbon bond. And of course, the result is formation of new carbocation, because as pi electron pair has left, the other carbon of the pi bond is now left electron deficient. Keep in mind duet rule. Hydrogen atom is capable of forming only one bond. So if it forms a new bond, then the old one has to be simultaneously broken. So it's a common mistake pushing electron pair on hydrogen without breaking the existing bond. So if electron pair is moved to form a bond to hydrogen, the existing bond to hydrogen has to be broken. And so those two curved arrows, of course, follow each other head to tail. And so you can see in the first example, for example, OH bond is formed and HBr bond is broken. In the second example, again, OH bond is formed. Now NH bond is broken. And note where electron pairs end up. In the first case on bromine, in the second case on nitrogen. In the final example, that's protonation of a double bond. So pi electron pair forms bond with hydrogen. So one of the carbons of the double bond forms bond with hydrogen. The other carbon will be left electron deficient as carbocation, as in the first example. And a hydrogen-bromine bond is broken to give bromide anion. Of course, octet rule also has to be obeyed. So when pushing electrons using curved arrows, make sure to obey octet rule. So second row atoms are capable of forming only 4 bonds. They can have only octet field. So if an additional bond is formed, one of the existing bonds has to be simultaneously broken. So in the first example, nitrogen free electron pair forms bond with carbon. That means one of the bonds to carbon has to be broken, and it's the weakest bond. It's carbon-bromine. So in the products, we have nitrogen-carbon bond that has been formed, and bromide anion, which took a free electron pair with it, and now it's Br minus bromide anion. In the second example, we have hydroxide anion that forms bond with carbon, and now it's carbon-carbon pi bond, pi electron pair that is moved to oxygen atom, and we have resulting example, tetrahedral carbon, carbon with 4 bonds, and negatively charged oxygen with 3 free electron pairs. Again, make sure that you know where electrons end up as a result of indicated movement by curved arrows. So make sure that you know which bonds are formed and which free electron pairs end up on which atoms. Now, students frequently use curved arrows incorrectly. So here are some examples of common mistakes by students. For example, using curved arrows to move charges, to move atoms, or to move electrons to an atom with field octet. So in this example, curved arrow is used to move a charge. Curved arrow starts on a negative charge. So that's wrong. Curved arrow should start on a free electron pair. Even though it appears to be a small difference, example on the left is wrong, one on the right is correct. So curved arrows are used to move electrons. So curved arrow has to start on electron pair, a single electron if it's fishhook arrow, or on a bond, because bond is composed of electrons. And of course, it ends up at the point where the bond is formed to, or where electron pair ends up on the atom, where electron pair ends up. Again, don't use curved arrows to move atoms. So in this example, curved arrow is used to move an atom, and that's because curved arrow starts on hydrogen. So that's wrong. Correct is for curved arrow to start on carbon-hydrogen bond. Now curved arrow indicates movement of an electron pair, and that's correct use. Again, another example where curved arrow is used to move an atom. So curved arrow starts on oxygen, while electron pairs, free electron pairs, are drawn away on the other side. Now, this is sometimes a little bit subject to debate, because showing of free electrons is optional. And sometimes some authors will not show free electron pairs, and will use curved arrow like this, and then that's appropriate use because we understand there is free electron pair on oxygen. But this example is wrong, because free electrons are shown. And if free electrons are shown, and you should show free electrons in cases like this, So if free electrons are shown, then curved arrow must start at a free electron. So here is correct use, where curved arrow starts at free electron pair and ends up on hydrogen. Here we have some other examples of moving atoms. So here curved arrow is used to move hydrogen, and actually the actual movement of free electrons is the opposite, in opposite direction, from nitrogen to hydrogen. So in this case, use of curved arrow is completely wrong. There is an attempt to move a nucleus. And that's understandable why a student would do that, because after reaction is over, nitrogen forms bond to hydrogen, and OH bond is broken. This curved arrow is not shown, but this first curved arrow on the right should be accompanied by another curved arrow that shows movement of OH bond. That electron pair, OH bond electron pair, is moved to oxygen. I didn't show it to avoid any confusion. I only wanted to show the mistake and correct arrow. So it's understandable why a student would make a mistake like this, because it appears that as a result of the reaction, it's hydrogen that moves, because when we write reaction products, we will write NH and O- as products. So it appears that hydrogen has moved, and so it makes sense that one would use arrow to move hydrogen. Nonetheless, that's completely wrong. Curved arrows are only used to move electrons. Curved arrows, of course, should not be used to move electrons to an atom with an octet field, unless there is simultaneous bond breaking. So here is one example where molecule of water reacts with ammonium cation, and curved arrow is used to move free electron pair from oxygen to nitrogen. That's not possible. The reason why a student would make a mistake like this is that positive charge is on nitrogen, and so it makes sense to move electron pair to positive charge, but that's not where the bond is formed. Nitrogen already has octet field and cannot accept any more electrons. So free electron from oxygen flows towards hydrogen, and OH bond is formed while nitrogen-hydrogen bond is broken. So here we need two curved arrows, and so this is correct use. Here is another example, a little bit more complex, where the curved arrow is used to move pi electron pair to form new carbon-carbon pi bond. But problem is that the other carbon of that newly formed carbon-carbon pi bond also already forms another carbon-carbon double bond. And so it would end up with 5 bonds. So this, as written, this is wrong. So the way this should be, one way that this could be written is that this pi electron pair is moved to the carbon atom to form carbanion, carbon minus, with free electron pair. So that would keep all the octets filled, but no atom would exceed octet. And finally, just as a summary, I'm going to review here different types of arrows that are used in organic chemistry. Not all of them, but those most commonly used. So full curved arrow indicates movement of electron pair. Curved half arrow or fishhook arrow indicates movement of single electron, and there are some other arrows that you need to know. Reaction arrow, of course, is straight full arrow. Equilibrium arrow are two arrows that point in opposite directions. They could be either full arrows or more commonly half arrows. There is no difference whether we are using full arrows or half arrows pointing in opposite directions. It's only a matter of convenience, because half arrows are often cleaner and easier to draw. Drawing appears to be cleaner. Resonance arrow, don't mistake that for equilibrium arrow. Resonance arrow is double-headed arrow, and it actually indicates movement of electrons in space, electron delocalization. So make sure to distinguish that from equilibrium arrow, very different concept. And then we have a retrosynthetic arrow. This is kind of block arrow, and you probably won't encounter it much. This is used in analyzing how to make a compound, when carrying out analysis, how to make a compound, how to synthesize a compound. And then arrow like this indicates that actual reaction is going in the opposite direction, that it's going backwards. Finally, two curved arrows that are touching indicate coupled reactions. So these coupled arrows don't indicate movement of electrons, since they are two curved arrows that are touching, so it's not a single curved arrow. They indicate coupled reactions, and they're not used that much in organic chemistry, but they are used a lot in biochemistry. So you will probably encounter that when you take a biochemistry course. This completes our review of arrows, particularly curved arrows in organic chemistry. And next, we are going to examine free radical reactions.